here we go. You get to learn the second derivative rule of your entire life, and it's going to be the product rule. Now, you recently learned the power rule, which you see right here, which is really nice and tidy when you have a polynomial. But what happens if your equation doesn't look like a nice and tidy polynomial? If you had to try the power rule on this, you would say, huh? No chance I'm going to get that done. Well, there's a thing called the product rule that's going to come to our rescue, and even after today you won't be able to do this derivative because we have to learn some things about trigonometry and natural log derivatives, but you will see later on, once we learn some extra rules, how the product rule comes in to save the day when the power rule is useless. And now over here in the purple, you see the product rule. And you don't like what you're looking at because it's math symbolism and people have a natural aversion to math symbolism, but we're going to fix that by doing a couple of examples. But the big overview is this. If my function can be thought of as two functions multiplied by each other, then I get to follow this pattern. The derivative is the derivative of the first piece times the second, plus the first piece times the derivative of the second. So you can see how in this problem over here, it is two functions multiplied by each other. So when you someday learn the rules for trigonometry derivatives and natural log derivatives, you can apply the product rule. So here's an example problem where we can follow the product rule, and you can see how these big ugly symbols turn into a very understandable pattern. I see a function that is one function times another function. My advice to you is go ahead and put these little brackets to separate the two functions in your mind so that you can easily follow the pattern. And since the square root of x is not very conducive to doing the power rule, which is going to happen inside the product rule, I would do an eyeball adjustment because the square root of x is really an x to the 1/2. So now I'm going to follow this pattern, which once again says derivative of the first times the second plus the first times the derivative of the second. You may need to pause the video, but check this out. Derivative of the first times the second plus the first part times the derivative of the second. And if you want, you can do an eyeball adjustment. I did that eyeball adjustment, but that makes it really no better or worse than the previous one. The only way this would be more useful is if I had to do further calculations. Like, what if I was asked, what is the slope of the tangent line to this function y at x equals 4? Well, this being the derivative, or this being the derivative, is the formula for the slope at any point we care about. Apparently we care about the slope at x equals 4, so I have to be very careful with my symbolism. I have to say I'm now finding the derivative at x equals 4. Let me slide that up. So the derivative at x equals 4 is my derivative from the product rule with the 4 put in everywhere there's an x. So I start to crunch these numbers and then they turn out to be very big. So I'll just assume that you could crunch those numbers. Whatever that number ends up being, that's the slope of the tangent line to that function at x equals 4. I've got one more example for you. Here we have function c that happens to be using variable a, or c of a. As a reminder, we're going to follow this pattern because I see one function multiplied by another. So I'm going to show you both sets of symbolism here. If I called this function c that happens to be using variable a, I could use the symbolism dc dA, thank you Leibniz, or I could use c prime of a, thank you Newton. Regardless, derivative of the first times the second plus the first times the derivative of the second. That looks like a big mess. You would be totally allowed to leave it like that, but odds are you're going to end up having to do something extra with these derivatives as we learn more things. So maybe you want to start tidying this up. When I do the multiplying of these two terms and the multiplying of these two terms, it turns out that I have a to the fourth as common terms, so I can add those together. 4.5 a to the fourth and 3a to the fourth is 7.5 a to the fourth. Okay, so you know the product rule. But also, a few people out there said, "Hey, Mr. Hewland, what are you doing? You could have taken this original equation and multiplied it together so that what you have is 3 halves a to the fifth power. This thing times this thing is 3 halves a to the fifth power. So all I've done is an eyeball adjustment, made it look different. And from there, you could have done the power rule. I agree with you totally. So I take the original equation that at first we were going to do product rule. Instead of that, I say, you know what? Let's multiply across, and from there, use the power rule. And I get the same answer I did with product rule. So you're going to find this occasionally in derivatives, that you can go with whatever rule you like best for the situation. There's the product rule. Stay tuned soon for the quotient rule.